Hi folks, this is Heath. We're reviewing today for exam 2. Let's go ahead and get started. So the exam is this Monday. There's no class Friday. The university is giving you a 3-day weekend. So you have all the way from now until Monday to finish preparing for this exam. You choose the location just like last time. You can start anytime between 9 a.m. and 7:30 p.m. The exam is open until 9 p.m. But since you have 90 minutes to finish the test, you want to back up 90 minutes from that start time. Canvas will allow you to start at 8, for example, but if you start at 8, then you only have 60 minutes to start the test. So don't do that. You're just hurting yourself. So make sure you get started no later than 7:30. And then once you start, you've got 90 minutes to finish. That includes time to scan your work. Some of you messed this up last time. Used up the 90 minutes and then weren't able to submit your work. Please try to get your work in on time. Okay. You may use a scientific non-programmable calculator. You may use notes that you have written yourself. These are the same rules that we had for test 1. Please stick to them. I do not want to have to turn ugly over this. So, but you may use notes that you have prepared yourself, but you're not allowed to use any other resources. Okay? In particular, no online integration tools or anything like that. It's pretty obvious when somebody has used one of those and the form of the answer is not anything like an answer that we've generated in class. They tend to generate answers using more complicated forms. So please don't do that. So let's work through some of the practice problems here. Okay? We want to integrate this expression, and this is given in the order dy dx, which expression in the order dx dy also equals a. So let's draw what we're looking at here. Our bounds are x equals 0 and x equals 2. And then y equals x squared and y equals 2x. Y equals x squared is a parabola. And y equals 2x is just a straight line, goes to the origin with a slope of 2. And we're only going between x equals 0 and x equals 2. When x is equal to 2, this is the point 2, 4. And so y is equal to 4 up here. And what we're looking for is the region right here in between. Okay? So if we set this up in the other order, dx dy, y-coordinate takes constants, which go from 0 to 4, and the x-coordinate enters at the straight line. This is the line x equals y over 2. And the y-coordinate ends at, or the x-coordinate ends at this curve, and this is the curve x equals the square root of y. And then the function itself doesn't change because we haven't changed systems like going from rectangular to polar. If we went into polar, we'd have to multiply this function by r, but we're just switching within the rectangular system. And so this is choice C. All right, let's move on. We wanted to find the volume of the solid bounded by these surfaces. Y equals x squared, z equals 0, and 2y plus z equals 2. So let's sketch this out. Y equals x squared is, once again, it's a parabola in the xy plane. And since z is not included in this surface, this parabola extends forever into z direction. And so that's what that surface looks like. Z equals 0 is just the xy plane down here. And 2y plus z equals 2, I'm going to rewrite that for a moment as z equals 2 minus 2y. That's a line in the yz plane that starts at z equals 2. That's the z-intercept. And then the slope is negative 2. So it's going to drop down 2 and move 1 over in the y direction. And so it's going to cross down here at z equals 1. And this plane, or this line, because the x coordinate isn't included, extends in the x direction and creates a plane. And this plane and this cylinder interact, and what we've got here is, I'm going to draw this separately. A shape kind of like this. Let's erase that part there, see if I can do this. So it's got a parabola for the base, but it's got a flat plane for the top on the shape. That's the shape that we're looking at. And we want to figure out how to integrate this in the order dz, dy, dx. So we need the largest and smallest x coordinates on this shape. Well, the x coordinates are where the parabola and the plane cross. So we know that down here z is equal to 0. And since z is equal to 0, 2y is equal to 2. So y is equal to 1. Z is 0, y is 1. And since y is x squared, x is going to be positive 1 up here and negative 1 back here. And so the largest and smallest x coordinates are negative 1 and 1. All right. So then we'll set up the middle coordinate, dy. In a triple integral, we need a wire to set up the middle coordinate. The wire is going to extend in the z direction, and it's going to move in the y direction into this shape. We can't control the placement of this wire. It might enter the shape at the front of the shape, for example, and cut through the shape like so as it slides through, or it might enter the shape right at the middle and cut through the shape like so. But we don't know for a fact that it's going to hit at y equals 0. It might hit at one of these y coordinates. But no matter what, it enters along this curved surface, y equals x squared. And as it pulls through, regardless of where on the surface it enters, it always leaves along this line right up here. And along this line, y is equal to 1. And then the last coordinate is the z-coordinate. So now we're just going to shoot an arrow through the shape. The arrow will enter along the bottom at z equals 0 and leave across the top, which is this flat surface, 2 minus 2y. And that gives us choice C. All right. Let's keep going. We have a rectangle whose vertices are zero and negative 1. All right, so that's 0 in the x direction, but negative 1 in the y direction. 2, negative 1. 2, positive 1, and 0, positive 1. So there's our rectangle. And then we have this function xy squared that lies over this surface, okay? And it's a function that kind of comes out like so. But you don't need to know exactly what that shape is. The question is to find the average value. The average value is equal to the integral with the function I'll just say dA for area. We can choose whether to do this dy dx over just the plane area itself. Okay? So this is the volume divided by the area. Well, in this case, we don't actually need the calculus to find the area. The area is also base times height, because this is just a rectangle, and the base is 2 and the height is 2. So the area is 4. That saves us having to do one of the integrals. But we are going to have to do the other integral. Since it doesn't really matter for a rectangle which order we integrate, we'll do dx dy. Y goes from -1 to +1, and x goes from 0 to 2. We'll do the inside integral first. The integral of x is x squared over 2. Plugging in 0 and 2. 2 squared over 2 is 2y squared. And 0 squared over 2 is 0y squared. So we just get 2y squared. So now we have to integrate that from -1 to 1. And so we get 2/3 y cubed. Plug in 1, plug in -1. Oh, all right. So when we plug in 1, we get 2/3 times 1. And when we plug in -1, we get 2/3 times -1. And 2/3 minus a -2/3 is 4/3. That's the volume. So the volume over the area is 4/3 divided by 4, and that's just 1/3. And that's choice B. Okay. Moving on. Let's another rectangle problem. This time my rectangle goes from 0 to 1 in the x direction and 0 to 1 in the y direction. Let's see if we can do that. This rectangle is being partitioned into 2 subrectangles by the line x equals 1/2. So here's 1/2 on the x-axis. The question says to use this partition and the midpoint rule to estimate this integral where we're integrating the function x squared. All right, so we have to use the midpoint rule, so the important points are these 2 points right here. This point, the x-coordinate is the midpoint between 0 and 1/2, so that's 1/4. The y-coordinate is the midpoint between 0 and 1, so that's 1/2. And the z-coordinate is this function here, z equals f of x comma y. X squared is 1/16. Z equals x squared. And so we have this very short rectangle here. Rectangular box that's only 1/16 of an unit tall. Okay? That's our first box. Then for our second box, the midpoint is between 1/2 and 1 on the x-axis, so that's 3/4. The y-coordinate is still the midpoint between 0 and 1, that's still 1/2. But now the z-coordinate is 3/4 squared, which is 9/16. So this box is much taller than the first box was. In fact, it's 9 times as tall, and I haven't really drawn it quite that exaggerated, but it's a much taller box. And so the estimated volume is the sum of the two boxes. So length times width times height for each box. Now be careful, these coordinates themselves are not the length, the width, and the height in most cases. The length in the x direction goes from 0 to 1/2, so that's 1/2 for the first box. The width goes from 0 to 1, so that's 1 for the second box. And the height goes from 0 to 1/16, which is 1/16. That's the height of the first box. Plus length times width times height for the second box, so that's 1/2 times 1 times 9/16. And so we end up getting 1/32 plus 9/32, which is 10/32, which reduces to 5/16. And that's choice C. All right. D is the region inside the circle x squared plus y squared equals 4. That's the circle of radius 2. And we want to integrate this function around the circle. All right. So in polar coordinates, r and theta, theta goes from 0 to 2 pi, which is this integral here, 0 to 2 pi. And the radius starts in the center and goes outwards and always ends at 2 because we're just integrating over a circle. Now that doesn't help because all of our choices go from 0 to 2 pi, or 0 to 2, except for the first two choices. Those two are wrong. So what we have to look at is what's going on inside this function. And what we have is x times the square root of x squared plus y squared. Well, x is r cosine theta, and the x squared plus y squared is r squared, but the square root of r squared is just r. And so we get r squared cosine of theta. But when polar coordinates, we also have to multiply by r. Multiply this by r to put it in polar, so we put this down as r cubed cosine theta. And that's where we get choice E from. Not from setting up the geometry, but from setting up the inside function, the integrand. Okay? Let's keep going. Oh, let T be this tetrahedron. 0, 0, 0, 2, 0, 0, 1, 1, 0, and 0, 0, 1. Okay? So let's draw this out. Here are my vertices. There's the origin. That's 0, 0, 0. 2, 0, 0 on the x-axis. 1, 1, 0. So that's 1 unit out in the x direction, 1 unit over in the y direction. And 0, 0, 1, which is up here in the z-axis. So those are my four corners. We build a tetrahedron with these four corners. and we want to know what the volume of this tetrahedron is. Now, I got this problem off of an old final exam, and whoever wrote this problem was needlessly cruel because two of the options are in this order, dz dx dy. One of them is in the order dz dy dx, and one of them is in the order dx dy dz. And so it looks like we have to do 4 different orders to do this. Okay? And so what I'm going to do is I'm going to not completely solve the problem, but I want to show you how to eliminate some choices here. The outer boundary is constants, and y definitely goes from 0 to 1 because this point right here has a y coordinate of 1. X, on the other hand, goes from 0 to 2 because this point has a 2 on it. And so just by looking at the endpoints, I know that this one is wrong. And so that eliminates one of our choices. And so what I'm going to do now is I'm going to set this up in the order dz dx dy. If I get choice A, the answer is A. And if I get choice B, the answer is B. And if I get something else, then by elimination, the answer is going to be choice D. So that's how I'm going to eliminate my choices here. The answer is going to be D because I've done this problem before. But I'm going to show that the answer is D by eliminating that it can't be A or B. So we're going to set this up in the order dz dx dy. Y are constants, and our constants in this case are 0 and 1. For the middle interval, we need a wire. My wire is going to extend into z direction. So it's going to go up and down. But it's going to travel in the x direction. And so it's going to enter along the back of this tetrahedron here. Okay. Now, this back of the tetrahedron goes from 0, 0 to 1, 1. It connects this point to this point. So if I just look at those two coordinates, x and y, what equation connects 0, 0 to 1, 1? And that's the line y equals x. Or same thing as x equals y. And so when I have to say what x equals, I'm just going to put a y down here. So this part is okay. That's good. Then the front end, where the wire is going to stop cutting through the shape, is going to be right at the front of this tetrahedron along this line. And this is the line that connects 2, 0 to 1, 1. And I'm just using the x and the y coordinates because I just want to set x in terms of y. And the line 2, 0 and 1, 1. What's the equation of that line? Well, that would be y equals 2 minus x. Oh no, I didn't do this right. That's 0, 2 and 1, 1. Two 0 is over here, and 1, 1 is this point here. And if we extend the line, it does go through 0, 2. And so it's still the equation y equals 2 minus x. I just drew the picture wrong. There we go. All right. And so, except I have to say what x is. X is 2 minus y. Not, y is 2 minus x, but x is 2 minus y. And so that eliminates this choice. It can't be B. So far, A is still looking pretty good. But now we have to talk about the z coordinates. If I draw an arrow going in the z direction It will enter the tetrahedron down here at the bottom at 0. And it will leave the tetrahedron along this surface here. Oh, and now we have to do a little bit of work, because we have to find the equation of this plane. So let's call these points A, B, and C. I'm labeling them in the order that they're given to us in the problem here. Okay. The vector from C to A goes forward 2 units, 0 units in the y direction, -1 unit down. The vector from C to B goes 1 unit forward, 1 unit to the right, -1 unit down. That cross product is 0 minus a -1, -2 plus 1 is -1, but we change the sign and make it +1. And 2 minus 0 is 2. And so we get x plus y plus z plus 2z, is equal to a constant. Well, x plus y plus 2z is going to equal 2. And that checks with both points A, B, and C. And so 2z is equal to 2 minus x minus y. And so z is equal to 1 minus 1/2 x minus 1/2 y. But that's not what we got up here. It's what we got down here. Choice A had the right limit here, and choice B had the right limit here. But neither choice has both limits correct. And so by elimination, the answer needs to be choice D. Okay? All right, let's keep going. Let's describe this solid here. Okay? So my bounds are theta equals 0, theta equals, I'm sorry, not theta, phi. Phi equals 0, phi equals pi over 3, theta equals 0, theta equals 2 pi, and rho equals 0, and rho equals 3. Okay? All right. So 0 to pi over 3 means that we start at the z-axis. That's where phi equals 0 starts. And we sweep down 60 degrees to an angle of pi over 3. And we get this triangle. Theta equals 0 to 2 pi says that we take this triangle and we wrap it all the way around a circle of 2 pi. And that looks like a cone, but then the radius goes from 0 to 3. And so what that's telling us is that in the radius direction, I always go out 3 units no matter what my angle is. So I go 3 units this direction, and 3 units this direction, but then 3 units in this direction, 3 units in this direction, and so I end up getting a curved top on this cone. So it's not a cone with a flat top, it's a cone with a curved top. It's inside the cone, but it lies under a sphere of radius 3. This curve being part of a sphere. Okay? And so that's what's going on here. We get a shape that's kind of like a snow cone. All right. We're given this information about the lamina, and we want to find the center of mass for the lamina. So the center of mass, which our book notates as the point xy, but with lines over the x and a y, is the point. The notation is confusing here. It's my over m and mx over m. But my is the integral we get when we multiply x times the density function. And m is what we get when we just integrate the density function. And then mx is the integral we get when we multiply y times the density function over m, which is just the integral of the density function. So this doesn't have a density function in it at all. This was not going to be helpful for the region. This tells us the area of the region, but it doesn't tell us anything about the mass of the region. What we're going to need is, for the x coordinate, we're going to need this value divided by this value. And for the y coordinate, we're going to need this value divided by this value, 6 over 3. And so that's going to be choice C. All right, the surface whose equations in spherical coordinates is theta equals 3 is... All right, well, 3 is a little bit less than pi. Theta starts here. Oh, and we're going to go around 3 radians, which is not quite halfway around, not all the way around to the back of the x-axis. And what's missing from this equation is there is no r and no z. So along this angle, we can go out any radius we want and any height we want. And so we can go as far out along this angle as we want and as far up along this angle as we want. And so we are generating a plane. We're fixed at going this far around from the positive x-axis, but we are not restricted into how far out or how far up we go. Okay? All right. All right, this expression, 0 to 2 pi, 0 to theta, calculates the area of which shape. If you're not sure, make a table. When theta is equal to 0, the radius is equal to 0. That's the origin. The origin is not part of this shape, so it's not going to be choice C. And then what happens as theta increases, pi over 6, pi over 4, pi over 3, so on and so forth, the radius just keeps right up with it. And so what happens is that the further we go around, the bigger the radius gets. And so the radius just keeps moving further and further away from the origin, causing the trajectory to spiral out. Okay? That's the idea. All right. Let's keep going. Find the volume by solid. Find the volume of the solid obtained by intersecting these two cones. So this is a cone z squared equals x squared plus y squared. This is a cone z squared equals 1, or actually, let me write it this way. Z minus 1 squared equals x squared plus y squared. With a negative sign. Let's see, you bring the 1 over, and then we still have to change the sign. Well, we're squaring, so that's okay. And so one of them is going to be a cone that sits at the origin and opens upwards in the positive direction. And one is a cone that starts at 1 and opens down in the negative direction because it's subtracting. And this is the shape that we have. Okay? So they intersect. The way we find where they intersect is we set these equations equal to each other. So we get square root of x squared plus y squared equals 1 minus the square root of x squared plus y squared. So we get 2 square root of x squared plus y squared equals 1 square root of x squared plus y squared equals to 1/2. Square both sides, x squared plus y squared equals to 1/4. And so that's the equation of a circle. We solve this as a circle whose radius is the square root of 1/4 or 1/2. So the radius of this circle is 1/2. Okay? So let's set this up in cylindrical coordinates, dz, dr, d theta. Theta goes all the way around from 0 to 2 pi. The radius goes out from 0 to 1/2. And the height, the z coordinate, enters at the bottom cone, which in polar coordinates this is an r, and leaves at the top cone, and this is 1 minus r. And because we're integrating in cylindrical coordinates, we multiply by r. And if we take the time to work through this integral, let's see what we can do here. We have to do the top integral first. So we're going to do, or the inside integral first. Integral of r with respect to z is just rz. Plug in 1 minus r and r. And so we get r times 1 minus r times r. And so this is r minus r squared again, which is r minus 2r squared. Now we're going to integrate that from 0 to 1/2. R minus 2r squared dr. So that's r squared over 2 minus r cubed, 2r cubed over 3. Plug in 1/2 and 0. 1/2 squared is 1/4 over 2 is 1/8. 1/2 cubed is 1/8 times 2/3 is going to be 1/12. And that's the same thing as 3 over 24 minus 2 over 24 is 1 over 24. So we then have to do the last integral from 0 to 2 pi of just 1 over 24. Well, that's 1 over 24 theta, evaluated at 2 pi and 0. And so we get 1 over 24 times 2 pi, and the 2 and the 24 reduce to 1 over 12 times pi, which is pi over 12. All right. Number 12, set up but do not solve an expression that will find the region inside the circle r equals 1. That's this big circle. But outside the circle, r equals sine theta, and that's this little circle here. So since we're only integrating inside the first quadrant, my angle goes from 0 to pi over 2 and not from 0 to 2 pi. As we draw a line from the center out to the edge of the region, we always enter along this little circle, which is r equals sine theta, and we leave along the big circle, which is r equals 1. And then we put an R in here because to find area, we usually integrate 1. But we have to convert to polar. Multiply by R for polar. I realize I'm kind of next up to the inset picture here. But that R, it comes from the polar coordinates. Okay. Let's keep going. 13. This region here. Oh, and this was a fun graphic to create, let me tell you. Lies above the xy plane, below the sphere x squared plus y squared equals 4. That's this surface here. It continues on. It's part of a sphere. And outside the cylinder, which is here, of radius 1. So the radius of the cylinder is 1, but the radius of the sphere is 2. All right. Set up a triple integral to find the mass of the region. So the theta goes all the way around this shape. Goes back around here. So that's 0 to 2 pi. If we pull a wire that starts in the z direction or extends in the z direction, but we pull it in the r direction, it's going to enter at the edge of the cylinder, and it's going to leave on this point right here, which is on the edge of the sphere. And so it's going to go from 1 to 2. And then if we travel in the z direction, send an arrow through the shape, it's going to enter at the bottom, which is at 0, and it's going to leave across the top, which is along this sphere. And if z squared is equal to, let's see, z squared is equal to 4 minus x squared minus y squared. That's 4 minus r squared, and so z is going to be the square root of 4 minus r squared. And that's where we get the upper limit, 4 minus r squared. And then we still have to set up all of the stuff that goes inside here. X is r cosine theta. Z stays the same. Z is just z. And then sine y is sine of r sine theta. And then because we're going in polar, we have to multiply by an extra r, so we get an r squared there. And that's where we get r squared cosine theta times z times sine of r sine theta. All right. Two more. This solid in the first octant is enclosed by the plane y equals 1 plus x. Okay. So let's talk about that plane here. That's when x is 0. Let me make a table. Let's do it this way. Y is 1, when x is 1, y is 2, when x is 2, y is 3, when x is 3, y is 4. That's this plane here. It starts at x equals 0, y is equal to 1. This is the point 0, 1, 0. And then as x gets bigger, y gets bigger also. And the z-coordinate is missing, so we can go up from that plane as much as we want. The other problem is, though, that we have this parabolic cylinder here. And that's When x is 0, y is 1. When x is 1, y is 0. When x is 2, y is 1 again. That's this curved piece here. Starts at 1, goes down to 0, comes back to 1 again, and then finally goes out to 4. When x is 3, y is 4, where it meets this line here. They both meet at this point here, 3, 4, 0. And again, there's no z in this equation, so this parabolic cylinder rises up in the z direction also. And in fact, because it's curved, it rises up and all the way around until it meets the top over here. And then it's bounded by this diagonal plane, z equals 6. 6 is actually up here, minus 2x. And so what's happening is, as we go further out in the x direction, the z coordinate comes down, and that's what's flattening this shape off at the top. Okay? Set up and evaluate an expression that will calculate the volume for this shape. All right. So we need to choose an order of integration. Because I don't want to try to solve this for x in terms of y, I decided to put x on the outside, so I never had to solve for x. So I chose the order dz, dy, dx. The x coordinates go from 0 to 3. 3, 4, 0 is this point right here where everything meets. And then we set up a wire. The wire extends in the z direction and moves in the y direction. It's going to enter the shape along this curved surface, x squared minus 2x plus 1, and leave the shape along this front surface, which is 1 plus x. And so, enter along the parabola, leave along the straight line. In the z direction, our arrows come up through the shape. It'll enter at the bottom where z is equal to 0, and then leave along this top surface where z is equal to 6 minus 2x. And now we'll just work out these integrals. Integrating 1 with respect to z just gives me z. So I plug in 6 minus 2x and plug in 0 and subtract, and I get 6 minus 2x. This is the messier integral. When I integrate this with respect to y, I get 6 minus 2x times y. So I have to multiply 6 minus 2x times 1 plus x. That's foiling. But then I have to multiply 6 minus 2x times x squared minus 2x plus 1. Let me write what's happening here. 6 minus 2x times 1 plus x minus 6 minus 2x times x squared minus 2x plus 1. And when I calculate that out, this is what I get. And I have to integrate that from 0 to 3. This isn't too bad, except for just working out the calculations. But when you calculate it all out, the answer is 13.5. Or, if you'd prefer, 27 over 2. All right, last question. Let's go ahead and finish this up. Let's rewrite this triple integral, dy, dx, dz, in this order here. By the way, example 4 in section 15.6 of the book starts with this answer and has you convert it this way. I'm having you do it the other way around, but that, in fact, this illustration came out in a book from this example. So I picked an example that had you rewrite the triple integral from this order to this order. We're just doing it the other way around. Okay? My boundaries are z equals 0. Let me make some room here. Z equals 0, z equals 1. x equals square root of z, and x equals 1, and y equals z, and y equals x squared. So if we draw these, let's draw the complicated stuff first. X equals z, square root of z, is the same thing as x squared equals z. So that's well, this is a little tricky here. Let's start with y equals x squared. Y equals x squared is a parabola here in the xy plane. Starts at 0, curves out. And then y equals z says that when we move in the z direction, says y and z are the same and y is x squared, then z is also going to equal x squared. And so this curve in the y direction also continues in the z direction. And so that's what's going on there. And so we've got this curved out, hollowed out piece in the back. Z equals y is just a flat plane. When z equals 0, y is equal to 0. When z is equal to 1, y is equal to 1. That's this point here. It's kind of hard to tell. But that's, there it goes, z equals 1. And then x equals 1 is just a vertical surface on the front of the shape. Okay? This, I think, is tricky to visualize. This is probably the hardest of the shapes on this test to see what's going on because of this curved part in the back, which is sort of away from our view. If we had a rotated view of this, it might be a little bit easier to see. So now we want to set this up in the order dz, dy, dx. Our x coordinates are just constants. We go from 0 to 1. Then our wire extends in the z direction, but it moves in the y direction. So it enters along here somewhere where y is equal to 0. And as it travels through the shape, it's going to hit this curve and then come back up here. That's going to be what happens. And it's going to hit that curve, y equals x squared, and that's going to be the upper boundary. Okay? And then in the bottom, in the z direction, we enter down here at the bottom where z is equal to 0. And we leave across this top surface here where z equals y. And so we get, that's where the y comes from. And since we didn't change systems, we're still in a rectangular system, we don't have to do anything with this function. We don't have to multiply it by anything or rearrange anything or whatever. That function just stays exactly the same. All right. Well, we're over time, and we don't often go over time on these videos, but I hope this was helpful. If you have questions, I have office hours on Wednesday and Thursday this week. Good luck. Have a good 3-day weekend, and good luck on the test on Monday. Take care.